Hello and welcome. Bill Judge with Monkworks here. I've got another video on tap here. We're going to run through my Oshkosh 2023 presentation before we get into Oshkosh 2024. Wanted to get it out there. I've given this presentation at a EAA chapter. I also was up in Alaska a few weeks ago for the same presentation, where I also got to see the raffle cub, where the Alaska Airmen's Association every year raffles off a super cub. And I donated a generator to go in that Super Cub. So Dashini Aero built out this Super Cub, and every year the Alaska Airmen's Association gives away one of them, and I was lucky enough to be part of that. So super happy with it. Alaska Airmen's Association has scholarships for people that want to become aviation maintenance technicians or pilots, and so, fantastic cause and a really super cool airplane. Dashini does beautiful work. I was very impressed with it. Got a handful of pictures here for you to check out. And they were super impressed with the generator. So they're telling me that all their future builds will include a Monkworks generator. So very excited about that. It's kind of tough to beat the lightweight and a few moving parts and reliability of the generator that Monkworks provides here. So anyhow, more announcements. I'm gonna probably be at Oshkosh 2024 and presenting home-built aircraft project management. So, what are the things you need to think about for managing a project for your home-built aircraft? From a project management perspective, how can you do better? And hope you guys all show up for that. Excited about that. And with no further ado, let's roll into the presentation here. So, reliable electrical systems. Quick primer from Oshkosh 2023. And nothing's changed about my bio here. Still double E, RV8 builder and pilot. Lots of hours on my RV, lots of hours overall in my opinion. I am the maker of the 30 amp, 2.6 pound vacuum pad generator for experimental aircraft. And if you want to get a hold of me, Bill at monkworks.com. Works great. So briefing notes, similar to my other notes here. This is for experimental aircraft only. I'm not your guy for certified aircraft. And this briefing only supplements doing your own research for aircraft electrical systems. This is a primer, so you're not going to learn everything here, but hopefully this will get you started in the right direction. This briefing doesn't qualify you as capable of anything other than putting up with a dull presentation from a lackluster briefer. That'd be this guy. So it's not a replacement for learning, and understanding best practices of aircraft electrical wiring. If you want to check out a good resource, Bob Knuckles has got lots of stuff written on the web, and he's got his Air Electric Connection book, and I highly recommend it. Again, just a high-level overview, and this isn't all you need, but this is a good start. I think that a reliable electrical system is critical for many of the experimental aircraft we fly. A lot of experimental planes now have electronic ignition, electronic fuel delivery. We fly IFR, and we're dependent upon our IFR radios and electronic attitude indicators and things like that. So if you are building an airplane and you want a reliable electrical system, hopefully I'll get you pointed in the right direction here. And a shout out to Dan Morris, RV Dan on Vans Air Force. Super helpful to me in putting together this brief, and super helpful for the past 20 years in helping me figure out what is good and what is bad about particular approaches to electrical wiring for aircraft. Patient and generous tutor and mentor for me for 2 decades. So. Prerequisites. Even before you get invited to the party, there's a bunch of things that you need to incorporate into your wiring scheme and how you do electrical wiring in your aircraft. Number one is use good quality wire. So Tefsel is the standard for aircraft. The outside of it puts up with quite a bit of heat. It's basically impenetrable to most of the chemicals you might find in an airplane. So wire with Tefsel, end of story. Next step, make sure that the wire can carry the current. So if it's going to be in a really hot area and run by your exhaust or something like that, then you may need to derate the amount of current you put through it. But basically the table on the right there will give you an idea of what kind of current you can run through that wire. Use quality terminations all around. say full metal sleeve there. What I mean is you want a crimp that both crimps the wires and then also crimps around the jacket. And that's critical, that the mechanical loads get transmitted to the jacket, so you're not depending upon the copper to carry the mechanical load of the wire being terminated or what have you. Pitch pre-insulated diamond grip is a Amphenol brand name, and a good place to start for ring terminals and Fastenal terminals is Google Pidge terminals. You'll come up with all kinds of results there. So the key thing though is, like I mentioned, you want to have a mechanical crimp that grabs the strands of wire, and again, stranded wire here, not solid, and then also a crimp that grabs the insulation jacket of the wire. And I got a couple pictures here, that show we got a strain relief here, and then right next to it the metal to metal crimp. And then if you have to do soldering, put heat shrink around it and then immobilize it as much as humanly possible, fairly far from the solder joint, because the solder will wick its way up through the stranded wire, and that's going to cause a problem in the long term. So immobilization. And then just for fun, I showed also like a D-sub type connector here. The strain relief is back here and comes from the shell of the connector. You got crimps here. There's heat shrink in here too, which is a nice added level of immobilization and insulation as well. But pretty much every termination you look at that's a good quality termination is going to have those two traits. It's going to have a strain relief, it's going to have a crimp. So enough about that. Use quality tools. Strippers. Happen to have a pair of strippers here, and a lot of strippers have these different holes in them, and they're labeled with different sizes of wire. And if you use these, a lot of times you'll find if you clamp down all the way and run it back and forth, what you're going to end up with is nicks in the wire you're trying to strip. And so I tend not to use these sized holes very often. What I do is I score the jacket at the point where I want to do the stripping, and I take the end part of this, which is like a pair of pliers, and bend the wire a little bit, maybe 2 directions, maybe 4 directions, depending on what it takes. And then you can use these little circle ones and just clamp down a little bit on the insulation, and it should slide right off. When you do that bending, it should break the insulation. So use good quality tools. I mean, you can do pretty good work with strippers like this. Do a couple test strips and make sure you know what you're doing, and you got a good idea before you dive in and start working on your plane. But if you do nick the wires, then cut the wire again and try it again, because you don't want to lose any of those strands, because instead of having a number 10 gauge wire, you'll have something that's smaller than that. That's not desirable. So when it comes to crimping, so there's all kinds of different crimps out there. So if you can kind of consolidate down just a few different crimps, then you don't spend as much on crimping tools, but try and get the right crimper for the job that you're doing. And there's some Chinese knockoffs that are reasonably effective, depending on how many crimps you need to do, or maybe you have a tool crib at your EAA chapter that you can dive into and get the crimpers you need. But really try and use the right crimpers for the job. All right, so now you've terminated the wire and you got the right size wire in place. The next step is you got to immobilize that wire, and you want it to not move anywhere along its length. So I say use zip ties every 2 to 6 inches. The closer you are to the engine and the source of vibration, the more frequent you want to use zip ties. And you can use lacing too. There's nothing wrong with lacing. And then I've even used RTV. Just the point is immobilize the wires. And again, I mentioned already, you can avoid solder, but if you have to use it, put heat shrink around it and try and immobilize it well past that point where it gets stiff from the solder being wicked up through the strands. All right, so now we've got the prerequisites out of the way. Before you get started into thinking about what your electrical system should look like, you should think about the mission of your aircraft. So is this going to be a day VFR around the patch kind of airplane, or a long distance IFR traveling machine? So are you thinking Pete and pole, like in the upper right there, where if you do travel and you end up getting there a day after when you intended, it's no big deal? Or are you talking about a serious IFR traveling machine like the Lance Air 4 in the lower right? Probably a big difference in the electrical system for those two planes, obviously. Know your budget. dual redundancy might be the gold standard, but it can be very expensive. So, understanding what you want out of the plane and then what kind of budget you have to work with is important. And then next step is, of that equipment you're going to buy, know what's critical, and understand what things you can deal with that and what things that you absolutely don't want to go down. Electronic ignition, obviously. If you have electronic fuel delivery, that's critical. IFR instruments, probably. Maybe you can have some of those instruments off of your critical list if you have redundancy. But if you don't have a lot of redundancy, then maybe you want all of it on there. And radios too, I think, are critical. So we'll talk about trade space between partial and dual redundancy. So dual battery systems, single and dual power source, that would support all these things here: the electronic ignition, fuel delivery, IFR instruments, radio transponder. How should the system work? So now we have a mission, like, well, how do we want it to work? And I have my own thought on this. Keeping in mind, I put a picture of a monkey looking through a phone book here. That's how you should think about yourself when you're flying your airplane. Like, if you have an electrical failure in your plane, it's going to be a rare event already, and it's going to be probably difficult for you to train to and prepare for. So you really don't want to be searching through a long checklist or something like that, or thinking back through your mind of, like, how did I wire this exactly? What switch do I need to flip? To me, that's not a place you want to be. So my philosophy is that you don't need to do anything immediately. There are a handful of times when you're flying your plane where you need to do something right now. You lose the engine after takeoff, like you need to slam the stick forward and keep airspeed. Okay, great. Other than that, the adage of the best thing you can do when there's an emergency is to wind your watch. I like that adage because there's a lot of ways you can make things worse, but by taking stock of what's going on, using your time, and thinking things through, you can keep yourself out of a bad way. So no immediate intervention is required by the pilot in command. You don't have to diagnose anything and figure out the right thing to do in any sort of a hurry. So you're not troubleshooting, and that's the last thing you want to do if you're in the soup, final approach fix, or running down short final or something like that. Next thing is no cascading failures. Where one thing is going to fail, it's going to cause something else to fail. You want some kind of level of isolation. And the example of a cascading failure I give is a guy had heard a story about a guy who had a belt-driven alternator in the front of his engine, a vacuum pad-driven alternator on the back of his engine. He thought he had dual redundant power. Loses the main, the backup kicks in so quickly that it snaps the shear coupling. Now he's going from thinking he had dual redundancy to no redundancy at all. So be careful about stuff like that. MunkWorks generator's got a ramp-up function where it comes online over the course of about a half a second, and you're not going to get a snap shear coupling from that. So, better requirement, you wouldn't be forced to land before your intended destination. So, I give the example of the East Coast. They get these omega fronts where a front is running up and down, across the mid-Atlantic area, and it causes low ceilings and IFR across widespread areas, maybe 500-mile radius or something like that. You take off out of one of those airports with the intention of flying to the Midwest where the weather's good. Well, now you have an electrical failure and you need to land in 35 minutes or 45 minutes or something like that because you don't have any kind of backup capability. Now you're in a bad way. The ceilings are low, you may be forced to do a low approach. It's a situation you want to avoid. So ideally, you're not going to be in a place where you need to land before your intended destination. And best requirement is you feel comfortable taking off again, perhaps a VFR to limp home, or even better, IFR. So we'll run through some systems that you may or may not feel comfortable doing that. And obviously, in the moment, what you do might be different than what you're planning for. There's no reason you're forced to continue your destination. If you have a failure and you want to land, by all means land. But there might be situations you get into where it's just inconvenient or something like that to land right away. So most airplanes have what we'll call the simple approach here. And I've got these cartoons here to try and get you acclimated with the symbols you're going to see on the next handful of charts, the schematic symbols. So we've got a battery, big huge battery, cranks the engine, got a master switch. I got the Frankenstein switch there. You got some fuses, and the fuse is attached to your loads, and then you've got some means of power generation. And generally, older airplanes and a lot of modern airplanes, this is what they've got going on. There's not much else there. So in schematic symbology, that's what this looks like. So again, I got a battery, got a master switch here, I got my fuses, power generation, and I've got loads. This is all you really need. And all these schematics are going to be going through here, just illustration purposes. You should do a detailed design in order to figure out what all the values of these things should be. And we'll talk about how you can do that kind of selection as we go through here. But let's talk about the advantages of this. It's super easy to install, easy to troubleshoot. If something's not working, there's only a handful of things that could possibly go wrong here. It's inexpensive and it's lightweight. So looking at the all-up weight here, you can get a lithium battery, weighs 4 pounds. Power source, if you use a MunkWorks generator, 3 pounds, up to 6 pounds, if you're using a traditional alternator. So overall weight, you can get away with 7 to 21 pounds here, which is pretty darn light. Disadvantages, I wouldn't have any flight critical items that are electrical here. Your radios also, when you're starting, might brown out. When I'm going on an IFR flight, I like to turn all my avionics on, get flight plans added, and be ready for the flight before I start the engine. And then once I do all that, I crank my engine. And if you do that on this type of system, a lot of times the battery voltage will go down below 10 volts when you're cranking, and that will probably brown out your radios when all that configuration I did in my Garmin 430 gets nixed. So not a huge deal, but it's kind of inconvenient. And the biggest deal of this whole thing here is that the battery really takes a beating from starting the engine. So cranking on a battery makes it less reliable. And what are the failure modes that could bring up? Well, reduced capacity is one. Okay, so I have less capacity in my battery, big deal. But another that doesn't happen very often but can happen is the battery shorts through. So the battery literally becomes a short. And this happened to Andy Finley when he was at Reno a few years ago. It's a little long, low voltage indication. Okay, alternator failure or something, I'm going to switch on my backup battery. And this backup battery just attached to the main bus, and since the battery was shorted through, all the power from the alternator, all the power from the battery, all that's getting dumped into the battery that's now shorted through. And he ended up landing on Pyramid Highway. So, if you think through how you have your electrical system set up, you can avoid those kinds of failures. So anyhow, let's talk about some means to do better than this single bus approach here. So what I call diode isolated critical bus here. It's like the previous schematic here, but I've added some things at the bottom. I've added 2 diodes that both come from the main bus and feed the backup battery and feed your critical bus. And so, normal operation for this thing, you've got the backup battery turned on, and that's the switch I turn on the ground when I'm trying to configure my instruments for departure. So that brings up my Garmin 430 and my IFR GPS. And the reason why you have 2 diodes is because I don't want all the current that's charging the battery to get forced through the switch. So that's why the second diode is there. Advantages here, the backup battery carries all your critical loads with no intervention required. So if you lose your main bus, boom, backup battery picks up everything. It's been attached to it all along. You don't have to flip any switches here. Like I said, both master, so the master's up here, and then the critical switch is here. Both of those switches are on in flight normally, and you don't need to do anything if anything happens here on your main bus. If something shorts all this to ground, like the battery or your alternator dies, all good. Everything that's critical is going to stay up and running. And then again, this stuff doesn't brown out because the current can't flow backwards through these diodes when you're cranking. You want to have enough battery capacity here to carry all your critical loads to your destination. So that's why I was saying you need to figure out your critical stuff and make sure your battery can carry you there all the way. So, okay, what are the disadvantages of this? We went through the advantages. Added complexity. The diode may need cooling, and you got an extra battery, so you're adding weight. So talking about weight, If you had 2 lithium batteries, 4 pounds each, because you need a reasonable amount of capacity on the backup battery, 8 to 30 pounds here. If you had AGM batteries, they're about 15 pounds each. Power, if you had a Continental engine with 2 vacuum pads, you could run 2 of my generators, it'd be 3 pounds each. And overall weight, you could be as low as 11 pounds up to 36 pounds. So still, you can build up a very lightweight system here and have pretty good reliability overall. Critical bus doesn't require any kind of intervention. Let's talk about how you could do a little bit better. Add a second power source. So what I've done here is taken the previous one and added an extra power generation source on the critical bus. So now I have the advantage that I can make this battery smaller, because all this battery really needs to do is to carry the load at times when I'm at really low RPM and my main and my backup don't have enough power to keep the bus up. So this battery could actually be quite a bit smaller, maybe 2 pounds or something like that. So, if you have a lighter battery, smaller battery, cheaper battery, less long-term maintenance costs. Like, these batteries need to be replaced on a reasonable schedule, and some of the cost of doing that is going to be lowered by having a smaller battery. Disadvantages: second power source adds weight and complexity. So you gotta wire all this stuff up and have a means to turn this on and off. So a little bit more wiring. What's the system going to weigh? So 2 of these things, a 4-pound battery and a 2-pound battery, so 6 pounds up to maybe 17 pounds. Power sources, 6 to 12 pounds. Total weight of 12 to 29 pounds. So looking at the previous one, for an extra pound here, we've got a little bit more robust system, I believe, and that you've got sort of triple redundancy. You've got your backup battery, and you've got your main battery, and you've got 2 power sources. So pretty robust system, and there are ways you could do even better here. And now what I've done is I've added a double pole relay that allows you to redirect the backup power to the main bus in the event that the main power source has failed. And the backup battery here probably needs to be bigger if you want to be able to have this get home capability, or you're going to be substantially limited if you do limp home with this capability. But essentially this rewires this system to look like this system here. Slide 8 becomes like slide 10 here when this is switched. So you can use a cube relay for this. Like, there's 40 amp cube relays off the shelf. You're using one of my backup generators, you've got 30 amps coming through there, so that's perfectly fine going through a cube relay. Okay, all up weight, batteries 6 to 17 pounds, power 9 to 12 pounds, and then 17 to 29 pounds overall. And again, this is a pretty solid way to get you home in the event that something fails and you're stuck in some place where you really don't want to do a field repair. Okay, so those are general architectures of systems. Let's talk about some component selection here. So first component to select is the battery. Let's talk batteries here. I've got some spec sheets from different batteries, or screenshots out of spec sheets for a couple different batteries here. And cranking size, you should be able to talk to all your fellow builders and they'll give you a good idea of what size you need to crank. Once you have that, that's your cranking battery. Backup battery, you got your list of critical items. Ideally, you put those on the bench and you run them and you find out how much current they burn. Review the spec sheets for the batteries you're intending to use and see if they're able to carry those loads for the periods of time you'd like. So let's talk about AGM batteries first. These are essentially lead acid batteries with a no maintenance type setup, and Odyssey is the one I've got up here now. So if you're only pulling a little bit of current through a battery like that, you can go 20 hours at 9/10 of an ampere, and that gets you the rating that you probably read on the label here, 18.3 amp hours. If you want more power out of it, let's say 5 amps, it can only go 3 hours. Multiply 3 times 5, you get 15 amp hours. So you've lost, 20-ish% of the capacity of the battery just because you're pulling more current. And it gets even worse as you pull more and more current out. If you want 16 amps, the capacity of the battery is down to 12 amp hours. You can only go 45 minutes. And 16 amps is probably a lot for critical loads, but something down in this 7 to 12 range is probably right, and you can only go an hour or two. And then be even more wary of this in that all of this is saying at the end of that 2-hour period at 7.1 amps, the battery will be at 10 volts. So you have to be very careful that your equipment's going to run at the voltage this battery is going to kick out. So lithium batteries, the degradation in capacity is not nearly as bad as you ramp up the current draw. And you can see here what the amp hour capacity looks like at different draw rates, and you can go from half of the capacity of the battery up to 1.5 times the capacity of the battery discharge rate, and you get some change in the capacity, but it's not nearly as dramatic as the almost 50% loss here, 33% loss or so. And the other thing that's beautiful about lithium batteries is that they keep their voltage up for a longer period of time. They do fall off a cliff right here at the end, and that's just the reality of it, but you're able to run useful loads for a lot longer. It's not this 10 volt voltage at the end of the capacity period here. So component selection. Let's talk about diodes now. Diodes should be your best friend here in trying to build a reliable electrical system here. The voltage rating only needs to be greater than the expected bus voltage. I've heard people talk about transients, and it doesn't matter. You want the voltage to go through it. The only thing you want it to stop it to do is stop it from moving is voltage going backwards through it when your main bus is down. So just enough voltage capacity to stop that. So this one here is rated at 40 volts. We got the part number there. It's good for 120 amps, actually 45 volts. It's got 2 diodes in it, so it works really well with his previous schematics. And I like this package too. The package is the form factor here. It's got screw terminals on top, so it works really well with your typical crimp ring terminals. And then the bottom is isolated, so you can bolt this to some beefy structure somewhere in your airplane. Particularly if you have an aluminum airplane like a Vans, like I've got, you're able to bolt that down to some beefy structure, and that's your heatsink. So anyhow, I really like this package. The next thing you want to look at is the voltage drop versus current. So the more current you pull through these diodes, the bigger the voltage drop is. But if you get a diode that's got a huge current rating like this one does of 120 amps, and you only pull 10 or 20 amps through it, then the voltage drop will be a lot smaller. And depending on what the temperature of the diode is, the voltage drop will change. But middle of the road here, you're talking somewhere between 2 and 5 watts that are going to be burnt off in power in that diode if you're running 10 amps through it. As you ramp up to more and more current, it's not a linear relationship. So tripling the current through it quadruples almost the amount of power that it's dissipating. And it may require you to do some experimentation to see how hot that diode gets under normal operations. So anyhow, that is a reasonable way to select a diode here, is understanding the voltage drop and how much all of your critical loads are, and then working through that. Also keep in mind that the current is going to spike initially as it's charging up the battery on the critical bus, but again, this diode is rated for 120 amps here, and it's transient, so it might get warm during that period, and then as the current peters off, and goes to steady state, then the amount of heat being dissipated through the diode will be less. All right, so architecture problem here. This is a schematic forwarded to me by a customer, and he was kind of cranky that I threw it in my brief here, but I think to me, it illustrates a system that I wouldn't want to have to deal with all of the potential ways that I could screw this up when I'm flying. You know, I've got one, two, three, four, five, six different relays. You got a contactor here, you got two batteries. So, you know, of course you can direct the power in lots of different ways here, but that means I have to make decisions about that. I have to diagnose a problem and then figure out the right action. I don't want to be in that position when I'm in flight. What I recommended you do is just replace all those relays with diodes. Like those two left and right engine buses, you want those to stay up all the time. You don't want them to ever go down. And so the diode takes care of that for you. And again, it's got some relays in there. So let's talk about relays really quick. Relays are great. If you're switching a large load like pitot heat or something like that, you can use a relay so you don't have to run that heavy gauge wire to your panel switch and then out to the pitot. You can run it directly from your bus wherever and not have to have as long of a run and not have to have that kind of power running up to your panel, which is nice. Keep in mind the relays all have a coil inside of them that magnetically moves the switch around for you from your remote location. And so you switch it on, current starts to flow through the coil, and current's now flowing through the coil. And the current in that coil is like water flowing through a hose. And you squeeze it, water starts to flow, and if you cut off the flow really quickly, you'll see the hose jump. And what's happening in the coil here is the energy that's stored in that magnetic field, it needs to be dissipated. And when the switch opens up, that magnetic field breaks down and it tries to get the current to continue to flow. And how it does that is by arcing across the switch. If you put that diode in there, now instead of the current arcing across here, the current's able to continue through the coil and then go through the diode back to the beginning of the coil and circulate until it dissipates. And then, you know, same deal for your contactors. You want to have this kind of a diode on your contactors. So you put the diode against the flow of current, and it will allow the current to dissipate. Okay, switches. All things being equal, if you go buy a mil-spec switch like this 8500 K1 from Eaton, it's environmentally sealed, it's got really good spec sheets, it's going to be 75 times more reliable than a commercial switch, but it only costs 15 times as much. So, you know, Amazon Finest at $2, this thing at $30. To me, it's a great deal. You know, you're never going to have to worry about this switch failing in your airplane if you run it within specs and don't fly a million hours before you decide to put it in the boneyard. You know, resistive loads are the easiest. You know, lamp loads and inductive loads are a little bit harder for switches to switch. If you're doing a lamp load like an old incandescent light, you should probably consider switching to LEDs. But if you are switching a lamp load, then you derate the switch by 75%, meaning instead of it being a 20 amp switch, it's a 5 amp switch. Inductive loads like your fuel pump or hydraulic pump for your gear, you derate by 25%, and then momentary switches like your flaps, you want to derate those by 50%. You can double the reliability. You can increase the reliability by putting a double pole switch and wiring the poles together. That increases the reliability, but don't depend upon that for increased capacity. Because as soon as one of those fails, the other one's going to fail shortly thereafter if you're not running it within the spec for just a single pole. And you also have to check it on a regular basis. You don't want to wire up a switch like that and then have one side fail and not realize it. So, you know, in order to get the reliability boost by doing that, you want to check on a regular basis. Current limiting. This is one of my favorite topics here. So, fuses. I like fuses. I've got fuses in my airplane only now. You know, I like these fuse blocks from Bussmann. You can slide in whatever size blade fuse you want up to a pretty high limit, 50 amps or something like that. And super lightweight, inexpensive, very reliable. And the thing I like the most is they're highly configurable. So if you want to add something new to your airplane, you don't have to drill new holes in your panel. You don't have to like piggyback onto another breaker that's already there you think isn't completely loaded. You can just grab another one of these terminals if you bought enough. You know, you buy one that's larger than what you need, and down the road, if you add something to your plane, it's really easy. So I like the configurability. Breakers, decent reliability. They're heavier. To me, they're really tedious to install. You know, they cost a lot more, and you know, cutting into your panel to add more circuits is no fun. Switch breakers, probably lowest reliability of all of these things here. And you're really only saving yourself the cost of the switch. They're still expensive, and they're still tedious to wire up. So I would avoid switch breakers. Electronic current limiting, there's some solutions out there that do electronic current limiting. It's pretty neat. You can reset the breakers. You can understand how much current each thing is pulling, which is nice to know. Customizable configuration of power things happening. You know that, okay, you know, your flaps of your gear come down at the same time or something like that. And you can do a lot of customization like that, which is neat. But it is a potential single point of failure. So keep that in mind if you go that route. All right, so example problem. Fuse blocks are your friend as far as I'm concerned. I pulled this picture off Van's Air Force, and like 28 breakers here, and you know, 28 times 30 is a lot of money. You know, the higher amperage ones are going to cost more, but I don't see the benefit in having all these breakers just so at every run up you can go, woo, look, all my breakers are in, because if one of them is popped, whatever it's running is not going to be running. So, you know, do your checks and make sure your stuff is working. You know, my panel, these are all my switches, and I had a field breaker here. I don't even have that anymore because I'm running 3 of my generators on my plane. I got master and critical, and I've got 2 ignitions. You know, human factor stuff, the switches that always stay on in flight, the master and critical and the ignitions, they're up on the panel where it's difficult for my hand to get to them. The switches I do actually touch are down on the mid-cabin console here. You know, the top one is nav and strobe. That one I usually don't touch too often. Got pitot heat after that, wigwag and landing light. And these are all in the same switch here. They're 3-position switches. So, you know, off, middle is navs, all the way to the right is strobes. You know, pitot heat's just an on-off. Wigwag versus landing light. So wigwag in the middle, and then all the way to the right is both taxi and landing light on. And finally at the bottom, again, human factors, easiest switch to get to is the fuel pump. So if I need the fuel pump in a hurry, I know right where it is. I don't need to read the label or anything like that. It's the very lowest switch in that mid-cabin console. So keep your human factors in mind as you're setting up your panel, and they'll pay big dividends in the long run. All right, that's the presentation. You know, key takeaways here, you know, use good technique, quality materials, and tools. Like, that'll get you 98% of the way there. You know, these electrical failures are relatively rare, but you can get rid of 90% of the failures that I've heard about and seen by just using good technique and quality materials and tools. You know, secure your wires in place, regular intervals. Every crimp's got a crimp and a strain relief. Immobilize your solder joints. You know, next up, let your mission drive your electrical system. You know, think through the failure modes of what you can put up with, and have a system that won't require you to do something immediately. That's my biggest contention. And diodes are your friend. You know, they're completely passive, you know, relatively inexpensive, and will work for the life of your airplane, and will save you lots of thinking, you know, when the time comes. And don't overcomplicate it. You know, this is, again, the single bus system is relatively reliable if you do use quality materials and good technique all the way through. So I appreciate you listening this far. Hopefully we're on tap for Oshkosh. Hopefully I get to see you there. And thanks for listening. Hope to hear from you. If you have any questions or comments, you know, by all means, hit me up, bill@monkworks.com. The phone number works as well. Hope to see you soon. Take care. Thanks.